In this video, I'll be showing the poscar file that I wrote that stores a list of coordinates and supercell dimensions and the information that is in a poscar file, and can read in poscar files and write them out, and has functions to manipulate the atoms in the file. So I'll show an example of how I would build a supercell to add a molecule to the system. So here I have a system that I'd like to make where I want to have this terphenyl on a section of the surface to have it run a little more efficiently rather than using some big rectangle. I want to select something like this supercell so that it's big enough that the molecules aren't interacting with each other. And I'd also like to have some bromine atoms close by to, this is again sort of representing a system that Pengui has looked at. So the poscar file has different functions that can help with that task. The useful ones start around here. So there are some simple ones to manipulate a list of atoms at the beginning. So to rotate, and here you have to specify an angle, and then you can also specify a list of the atoms in the file. So if there are 72 atoms or whatever, which specific indices that you want to rotate. And you can also specify a point to rotate around. The default is 0, 0, 0. Similarly, there's a shift function to translate atoms, where again you can specify a list. This also includes a new flag. Postcard files can be in one of two sets of coordinates, Cartesian with normal x, y, and z, or direct, where the positions are specified in terms of the lattice vectors. So the default behavior is that when you provide a vector to move the molecule by, it will move in the coordinates that the file is currently in, direct or Cartesian. Sometimes you want to move the molecule in Cartesian, so for instance by half an angstrom rather than half of a vector. So there's this additional flag that lets you do that without having to manually change. So earlier, somewhere in here, there's a function convert, which just switches what the object currently is from direct to Cartesian and changes the coordinates accordingly. There are some functions to remove atoms to the file and to add them. So here, again, you can specify a list of atoms based on their index to remove. There's also an option if you want to remove all of the carbon atoms, you can give the index in the list for carbon atoms. So it might be helpful here. Everything in the Python class is similar to what's shown here, with a list of atoms, and a list of elements, a list of the number of those atoms. If I show something else, you can see here there's multiple atoms in a list and then multiple numbers of those. So the variables that are in the Postcard class are similar. Can go up to the top where it's initialized, you have the same structure. You have an atom list and a number. And to refer to those, there are these functions, atom list, num atom list, cell, and so on. So if you just wanted to get this, then you would call this with something like that would give you, that would return the list. So a list equals this. I haven't imported this, so this will give an error message. And similarly for the other things. There's also a Boolean variable to indicate whether the file is in direct or Cartesian coordinates. These are both in direct, so that's true if it's in direct. This pos variable is the array, the NumPy array of all of the coordinates. I think I've explained most of this in the PowerPoint presentation. And there's also a copy function. So to continue through, keep is the opposite of remove. So you can specify a list starting at 0. So the first carbon atom would be 0, and then there would be another 54 carbon atoms, so up to index 53. And if you wanted to keep all of the carbon atoms, you could specify by type equals true here, and keep list equals 0 for the, because Python lists are indexed from 0. And if you wanted to keep the oxygen and the hydrogen, you could have a list with 0, 1, and 2. So that's just the opposite functionality as remove. There's a new function called addAtom, where you specify a type and then you specify coordinates in some way. You can either just give it a list with X, Y, Z coordinates, or you can take an existing atom in the Postcard file, the object, and specify an offset. And then there's this third variable which lets you specify a certain position in the list. So the default is that it will put it in second last, assuming that the last are surface atoms, which would be, this is more so something gas phase, but you can explicitly set this with this variable. There's a similar one to change atoms if you just want to replace one with a different type. Here, you have to specify the index of the atom that you want to change and the type of the new one. And again, if it's a new type of atom and you want it at a specific position point in the atom list, you can specify that. And so adding individual atoms would be a very tedious way of building molecules. So this function is one that I use quite a bit, which is to add two Postcard files together, or Postcard objects. So you would call it, usually I define some object called surf, and you would say send some Postcard file for the molecule. I often call it MOL. And if you just write this, then it will take the coordinates for the molecule atoms and it will just place them at that position in the file. It can be more useful to position it in reference to an atom in the surface Postcard. So to do that, you specify the index, the reference point of your surface atom, the index for the reference atom in your molecule, and some distance between them. You can also add an angle if you want to rotate the molecule when you do this. And that would be around this reference point specified by S index. This fixed aliasing is a little function where if you move atoms outside of your cell, it will do the necessary addition or subtraction to move them back in. This duplicate thing is not very important. And now we actually get to the input and output ones. Write, you just need to specify a path and it writes out that object, the object that you're calling it on, to that file name. You can also write an XYZ file if you want to view it differently. To read in, you would call the read function of the poscar package with a specified path, and it returns the poscar object corresponding to that file. Here, this main function is called when you run this poscar script, but not when you import it. And so I wrote a bunch of things to test the functions that I defined. And the thing that actually calls it is this piece of code here, which is common in Python. First of all, it lets you load everything in because Python is a scripting language. And so if it hasn't read your functions yet, then it will not know about them. So often in Python scripts, there's this snippet at the end and then a main function that calls all the other functions that you want to use. Here, because what I've defined is a class, I use it to run tests on that class. Okay, so with that explanation, now I'll show an example of how to make what I said I wanted to make. So if we go to VMD, the file I want to load is called, it's the 2D organometallic that I'm going to, oh, I need to change directory first. Go to representations and make it a ball and stick model. I need to open that here. So this is a file I had in a calculation before, and I just want to take these terphenyl atoms in the middle, and the most convenient way that I thought to do that is to first rotate it 30 degrees, so then I can just select based on X which ones are the right, which ones I want to keep. So that's what I started writing here. I will rotate and I'll comment out that because I don't need it at the moment. If I run it, so I wrote it to something I just called tempcar. You can see now it's rotated and can pick the carbon atoms that are farthest left and farthest right, so I know which values to keep. And I did this already, so I can uncomment this now. So it goes through all of the atoms. In this case, I did it by deleting the other ones. So if it's not in this range, it gets added to the list. And then it calls this remove. So I can run this again. I found what the problem was. I had apparently added a folder and a file to the Python path, and that's what it was loading when it imported poscar. So I've updated that now. And when I run this, there's no error. And if I load poscar or the tempcar file now, it shows the atoms that I wanted. I kept the coppers because I'll replace them with hydrogen. So that's index 30 and 31. So here I can comment out this line and uncomment the ones that I had before. Save that as a different file. It's called terphenyl. And if I open this, you can see it has hydrogens as it should. There is one funny problem with VMD where sometimes it will misinterpret your poscar elements. So you can see these are not hydrogens, but they're labeled as X. It shouldn't be a problem because VASP will read this correctly. So now I have the molecule that I can place above the surface. The surface file I wrote earlier is this. And I think if I put this hydrogen, or here it's considered X, number index 30, on top of this copper, that will be about what I want. So the surface index is 3. So I have a script to now add. It reads in the surface as a poscar object that I defined earlier. And here it has the index that I want, and I'll just put it 3 angstroms above this. And so this will write to terphenyl underscore copper. And can take a look at this. Seems correct. If I go to VMD and I load it in, moment of truth, it looks in the right direction, but somehow in going from between the coordinates of the molecule and the slab, it ended up rotated what looks like by 30 degrees. So if I go back here, then I can add my unfortunately this gets cut off. And I discovered a bug. So instead I will make a list. There are 32 atoms in the molecule. So I can then rotate those with the list and say the origin is the position of atom 30. Sorry, that's how that's called. So position returns a NumPy array with the parentheses open, and then square brackets are used to reference index, so I'm rotating this around the hydrogen. This time I didn't get an error. And my cat wants to come into this room. So that looks like it fixed it. This is where one case where this clone representations thing can be useful. So I can select the surface one, and now I get the same representation as the surface. So I can see this phenol is basically above this hollow site, centered above there, and each of the other ones is too. So that looks pretty good. Now I want to add some bromines underneath that are also at hollow sites. So I'll pick this index 89, and I'll go back to my script. So I'll define a new offset. So I picked a surface atom underneath, and so I just made the offset a little bit bigger. But I want the bromine closer to the surface than the molecule is. So I'll say this is 89, and then have it add a bromine. And I'll write this out to a different file. Let's see if this works. So I didn't get an error message, but I want to add the other. So 97 and 104. Because it added one atom, I need to add one to the index for each of these additions. It gives a sort of a warning message about where it's adding this, although it shouldn't do this for these new ones. What did I call this? So that loaded successfully, but I think there's some sort of problem because it is very small. Hopefully that fixed the bug. Let's see, that runs. And no, stop loading that. Okay, clone, aha. So basically, this looks like what I wanted, and now would be something ready to send, to upload. So you can double click on representations to turn them off. Gotta select the right one before making changes. So if we look at this now, we have the molecules and the bromine atoms close to each other, but that's okay because that's basically the state in the actual system. And these other terphenyls are far away.